Okay, here we are making videos again. I want to talk quickly about a couple of study goals in Unit 9. Number 10 might be obvious, but I just want to spell out a couple of words. You may not need a lot of notes. I just want to remind you that sustainability means different things for renewable and non-renewable things. Some things are renewable. Like if you cut down a tree, the tree could grow back. And if you take a salmon from the ocean, there might be enough salmon left to breed more salmon. So logs and fish are considered to be renewable. And the question for renewable items is, can you gather them more slowly than they recover, right? That would be sustainable. If the ocean gives you 20 tuna per year and you're only taking 10 tuna per year, then that would be considered a renewable harvest because you're taking it more slowly than it comes back. For renewable resources, sustainability is just about matching your input and output. We talked about this for groundwater. It might make sense for money, like a checking account. But sustainability for things that are non-renewable is kind of interesting. Like, think about how the modern economy works. We pull stuff out of the ground, we make it into something new, and when that thing is no longer useful, we make it into trash. And I just want to remind you that that's fundamentally not sustainable unless you keep finding a new thing to be useful. Like if we use up all of our petroleum stuff and eventually all the plastics get put into the ground, we could run out of plastics. And so we'll have to invent new stuff. You can't really keep consuming all the Earth's resources forever. So the one-way material economy is fundamentally unsustainable. This will come up a few more times in this unit. I'll probably just move on for now. Just wanted to revisit those terms really quickly. In number 12, you had two parts. There was the thing about the elements, and then there was the thing about the stuff that moves ingredients. I have some slides, but I want to warn you that different students come with a different amount of background in this topic. So you might need to do some Googling to bolster your background. If you want to be more knowledgeable, it'll kind of be up to you. In APES, it's kind of assumed that you're familiar with some basics. For example, you should know that the Earth has layers and that each of those layers is different, like a jawbreaker. Atmosphere, the crust is the part that we live on, it's solid rock. Underneath the crust is the upper mantle, that's magma. When the magma comes to the surface, it's lava. There's layers to the magma, and then we have a core inside the Earth. You should know that this is actually kind of funky. On a random chunk of space stuff, if gravity is just gathering dust to make a comet or to make a planet, usually that is just gravity bringing things together. The more dense will drop to the center, and the least dense will be on the surface. That's what you would normally expect. And on most planets, that is how the planet is organized, and they are, generally speaking, static. Except for collisions with space stuff, most planets are just perfect layers sorted by density. There's like a famous demo that you may have seen. I'm going to do my best to show you this. Forgive this clunky class time. Let's see if this works.
That are less dense than the beans. So this is a little bit more dense than the ping pong ball. And if you'll notice, as I shake it, the ping pong ball will come up before the heavier or more dense kind of tennis ball looking up.
Idea being that he's put two different things into a thing of beans, and one has less density, a ping pong ball, than the other. There's like a dog ball, a Kong ball.
So let me shake. Okay, again.
And I guess you could see, hopefully you could see, that the ping pong ball rose to the surface because it has lower density than the tennis ball thing, the dog toy. You would expect that on our Earth, you would have essentially a bunch of black beans, a layer of dog balls, and a layer of ping pong balls. That whenever the wind blows, the least dense thing would fall on top or whatever. But what's wacky is the Earth is not that simple. The Earth has a whole bunch of forces. It's interesting that we have water, but we have a whole bunch of forces that will shuffle our layers. So we have unusual distributions, different in each of the layers, not just sorted by density. Our crust is all the rock stuff. You'll need to know these. You can pause and write them down if you didn't get them in the homework. I believe this is in your book. And remember that if you include the core of the Earth, there's different ingredients. We have a mostly iron Earth, because if you include the core, there's a whole bunch of iron there. Again, you can pause this. And I think that the study guide also asked you to know about what's in the ocean. I didn't make a slide for that, I'm sorry. And then here's some of the stuff that you probably would need to know. First of all of these terms. You can ask me if you don't know. Make a note in your papers, and then you can ask me during class time after you watch videos. But I'm assuming that most of you have run into these at some point. The idea that rocks are eroded, moved around by water, that they settle to become sediment, that forms sedimentary rock over time, that sedimentary rock moves, and then that it changes when it heats up. That's called metamorphic rock. And maybe you know that igneous activity, where the rocks melt, makes volcanoes and new mountains and stuff. This is the basic rock cycle. You don't need to be an expert. The test is not about the rock cycle, but the College Board will assume that you know that rocks do cycle. So check these terms, make sure you got them. The College Board often asks about the different type of plate boundary. So look at my hands, please. In the speaker view, divergent is where boundaries spread apart, like we have at the bottom of the ocean. Convergent is where tectonic plates smash into each other. They converge, they come together. And usually when that happens, one of them has to win. So you'll have one going over the other, and that tends to make mountain ranges. That's usually the coastlines. And there are some places, if they're not coming together or spreading apart, they must be moving past each other. That's called a transform plate boundary. Like the San Andreas, the transform plate boundaries have a lot of friction that's released in bursts that we call earthquakes. You don't have to be an expert on any of that, but you do apparently need to know the three types of boundaries. The College Board asks a lot. So you should know that the planet has tectonic plates. You probably already knew that. Most of these were at the bottom of the ocean at some point, and then they're kind of smashing into each other to surface. Remember that sediment becomes rock. So sedimentation, the idea that you get layers, stuff was first moved by water and then chemically bonded into rock. You should also know that rock is going away. It's weathering. What you see in this image is kind of like what you see up at Lizard's Mouth. This is weathering by the wind. This is wind erosion. That's a type of of mechanical erosion. And these are terms that you have to know. Mechanical weathering is when something breaks something else. So wind-blown sand breaks sandstone. What we get at Lizard's Mouth, those are called wind caves, because wind is the mechanical force that wears away rock. There's also, you'll have to know this term, chemical weathering. Chemical weathering is like acid rain dissolving things. You can see that this rock has like a layer here that's a different color than this one. So this was the basic rock, but as it is encountering rainwater, there's a chemical reaction happening on the outside that can make the rock weaker. That's called chemical weathering. All rain is acidic, at least a little bit. So because all rain has carbonic acid in it. So all rain does a little bit of chemical weathering. You should also add to your notes that there's another type of weathering called freeze and thaw weathering. So you may have heard somebody explain how this changes the shape of rocks in like Yosemite Valley or whatever, where you'll have a layer. Rain will fall into that seam between layers of rock, and then when that water freezes, it expands. Then in the spring, that ice will melt and the rock will come loose. That's called freeze and thaw weathering. The idea that water works by gravity to get in between a crack. Once that crack has filled with water, freezing the water makes it bigger. It'll expand. So the change in temperature can crack a rock. And then when it warms back up a few months later, then it comes loose. That's called freeze and thaw weathering. It's kind of cool that water evaporates, and so it leaves behind crystals. Crystallization is a neat thing. It's caused by evaporation usually. And you don't need to like know every one of these words. It's not critical that you memorize this, but you do need to understand that ingredients on our planet are shuffled. They move, they cycle around. So I'll give you an interesting example, the history of this mountain. That mountain used to be corals. Those corals were ground up by fish, or they were powdered up by wave activity or hurricanes. They made a powder, a calcium carbonate sand. That calcium carbonate sand settled as a sediment, became sedimentary rock. The chemistry of that rock changed over time, interacting with water and pressure to make limestone. That limestone from the bottom of the ocean got thrust up into the air by tectonic activities and uplift. Now you have a layer of limestone up in the air, and that limestone starts to wear away because limestone is basic and all rain is acidic. And the only things that are left are the especially sturdy parts of that rock layer. Those are called the limestone towers of the Philippines. They're also found in Vietnam and Thailand. You don't need to be an expert on how this all happens. You just have to know that the ingredients on our planet get shuffled around, and you should probably know all that lingo. One thing I need to add is that there's these things called placer deposits. That's material that's, oops, I made a typo, sorry. That's material that's moved around in surface water and then left behind, you make a deposit when the water slows down. So, you know, like you get a river and a bunch of the sand moves, and then when all of that river slows down, the sand will settle. Remember that fast moving water can move really big stuff like houses and school buses and boulders and your mom. But as that water slows down, the heavier things will settle first. So the boulders are left behind at the top of the river, the rocks are left behind a little bit later, the pebbles are left behind a little bit later, and the sand is left behind right at the ocean. Those are called placer deposits when material is sorted by density as water changes speed. You probably want to write that down again. Materials sorted by density as water changes speed. This includes gold. So for anybody who's interested, I made a link to this slideshow about placer deposits and gold. I think it's super neato. And I don't know how much you have to know about placer deposits. You should know that it's associated with gold. You should know that it's water density, what I said earlier. But if you're into this, if you're just curious, check out this website. I made you a link in Neo. Finally, I'd like to add something. In study goal number 13, there's two separate terms, resource and reserve. A resource is anything useful. So silver is useful, it's a resource, it's something that we can kind of use on our planet. And sand is a resource, you need it to make concrete. And lead is useful, it's a resource that I use to make sinkers for fishing. That's anything that's useful. But a reserve is an economically viable clump. It's an amount that's worth getting. That's a reserve. And not all resources make reserves. I have two examples and then I'll stop this video. Silver is extremely common. If you walk down to the beach and you grab 1,000 pieces of sand, one of those pieces of sand will probably be silver. Silver is a very handy resource. We like to make jewelry out of it. Apparently it's good for spoons. Funny thing about silver, none of those processes I listed, none of this really gathers silver. So what's wacky about silver is it's a very common resource, but it doesn't really make reserves very often. That's why silver is expensive. It's not rare, it's just not found in economically usable gatherings. Lead, on the other hand, is, you know, another useful resource. But lead is organized by all sorts of processes, excuse me. It reacts with ocean chemistry. It does not erode very easily. It makes very distinct sediment layers because it's very dense. It melts really easily, so it's always found in certain types of mountains. So lead, finishing this point, is very easily found in reserves. That's why lead is cheap. Technically, there's more silver on Earth than there is lead. Silver's expensive because there aren't a lot of reserves. Lead is more rare than silver, but it clumps up. You find huge globs of lead all over the place, and you know where you'll find them. It's like a reliable pattern in rocks to find the lead. So not all resources make reserves. I will now stop my video.